Good day, everyone. Today we're moving from individual sequential circuits into full digital system design. Every complex digital system you'll ever build, a CPU, a peripheral controller, a communications interface, can be viewed as two interacting parts, much like a conductor directing an orchestra. One part does the actual work, and another part tells it when and how to do that work. We'll cover ASM charts, how to design the data processor, and how to design the control subsystem that drives it. And we'll carry one running example, a binary multiplier, all the way through to working HDL. Let's start with that conductor and orchestra idea and make it precise. The two-part structure every digital system shares. Every digital system splits cleanly into a data processor, or datapath, and a control subsystem, or controller. The datapath performs the actual work, arithmetic, logic, shifting, storing, and transferring data, using adders, subtractors, shift registers, counters, and multiplexers. It produces the system's outputs, and just as importantly, it produces status signals that report its internal condition back to the controller. The controller determines the sequence of operations. It generates command signals telling the datapath what to do, and it receives those status signals to decide what happens next. I like the analogy on this slide. The datapath is the hands doing the work, the controller is the brain telling the hands what to do and when. Notice the feedback loop in the diagram. Status signals flow back from datapath to controller. That loop is the whole reason state machines exist. With that partition in mind, we need a formal way to design the controller side, and that's exactly what the Algorithmic State Machine gives us. The Algorithmic State Machine, or ASM, is a method for designing finite state machines that was originally developed at UC Berkeley in the 1960s. At its core, an ASM chart is a special type of flowchart used to describe the sequential operations of a digital circuit. It determines both the sequence of events and the timing relationship between states. Think of it as a state diagram, but more structured and far easier to follow, because it specifies a step-by-step procedure for completing the digital design, the same way a software flowchart specifies a step-by-step procedure for an algorithm. That's exactly why ASM charts are so approachable if you've ever written pseudocode or a flowchart for a program. When you follow specific rules, an ASM chart is formally equivalent to a state graph, and it leads directly to a hardware realization. That's the key insight. ASM charts are the bridge between an abstract algorithm and a physical circuit. To read and draw ASM charts, you need to know the vocabulary, the three shapes that make up every chart. Every ASM chart is built from exactly three shapes. The state box is a rectangle. It represents one state and contains more type outputs, meaning outputs that depend only on being in that state. The decision box is a diamond. It tests a condition and has two, or occasionally more, exit paths, true and false. And the conditional box is an oval. It contains Mealy type outputs, meaning outputs that depend on both the state and the current inputs. If you remember nothing else from this slide, remember this. Rectangles are states, diamonds are decisions, and ovals are conditional. Mealy, outputs that only fire when a decision's condition is satisfied. Let's slow down and look at each of these three elements individually, because the rules governing them matter a lot once we start deriving hardware. Starting with the state box. It represents one state, with the state name in the upper left corner and, once you've assigned binary codes, the code itself in the upper right corner. More type outputs are listed inside the box, and critically, a state box takes exactly one clock cycle to complete, with exactly one entry path and one exit path. The decision box tests a condition built from one or more of the FSM's inputs, and it always has two exit paths, true, or 1, and false, or 0, which can lead to another state, another decision, or a conditional output box. Finally, the conditional output box holds Mealy type outputs that depend on both state and inputs, and it must always follow a decision box. You can only enter a conditional box from a decision box's exit path, never directly from a state box. Now that we know the individual pieces, let's see how they group together into a single, testable unit of behavior, the ASM block. An ASM block contains exactly one state box, plus all the decision and conditional boxes tied to that state. It has one entrance path and one or more exit paths, and it describes everything the machine does while it sits in that state. Look at the example on the right. State T1 increments A, then tests condition E. If E is true, a A conditional output clears R before moving to the next state. If false, it moves directly to the next state. The crucial point, and this is the one I want you to remember for synthesis, is that everything inside one ASM block, the state box operation and any conditional outputs, all executes within a single common clock pulse. The next state is simply determined by the binary values of the decisions made inside that block. With states, decisions, conditionals, and blocks in hand, we're ready for the actual design methodology, the 5-step process that takes you from an idea to working hardware. This 5-step process is the backbone of everything we'll do for the rest of this lecture. Step 1. Create an algorithm using pseudocode that describes the desired operation of the device. Step 2. Convert that pseudocode into an ASM chart, replacing each pseudocode statement with states, decisions, and conditional outputs. Step 3. Design the data path based on that ASM chart. Identify what registers and combinational logic you actually need. Step 4. Create a detailed ASM chart based on the data path you just designed, replacing abstract RTL notation with the actual named signals in your hardware. And Step 5. Design the control logic based on that detailed ASM chart. This is where you derive the actual state machine equations. Notice the philosophy here. This is a top-down approach, breaking a complex system into smaller, manageable blocks, each step building directly on the last. Step 3 asks us to design the data path. Let's dig into exactly how you go from an algorithm to real hardware registers. The data processor, or data path, is the hardware required for data manipulation. The adders, subtractors, shift registers, and counters that do the actual computation. It produces the system's outputs and, just as importantly, the status signals the controller depends on. Here's the practical rule for going from algorithm to hardware. Every unique variable that gets assigned a value in your RTL program becomes a register. What kind of register depends on what's being done to that variable. A simple assignment becomes a straightforward register. A shift operation becomes a shift register. A counting operation becomes a counter. And an arithmetic assignment becomes a register paired with combinational logic, an adder or subtractor. This table is your translation guide from pseudocode to hardware. Let's apply that translation guide to a real example. The binary multiplier will carry through the rest of this lecture. Here's the data path for a sequential shift and add binary multiplier. The multiplicand, register B, feeds into an n-bit adder alongside the accumulator, register A. The result, including any carry, C, combines with the multiplier register Q to form a single wide shift register, C, A, Q, which shifts right by 1 bit on every iteration. A counter P, sized log base 2 of n plus 1 bits, tracks how many iterations remain, and 2 status signals come out of this data path. Q0, the least significant bit of the multiplier, and P0, which fires once the counter reaches 0. On the right, note the 4 components that fully define this data path. The 2n plus 1 bit shift register, the n-bit parallel adder, register B, and counter P. Every one of these came directly from applying the translation rule on the previous slide to the multiplication algorithm's variables. With the data path as registers defined, we now need to formalize exactly what signals cross the boundary between data path and controller. This is the interface contract between controller and data path, and getting it right is what makes the 2-part design actually work. On the left, our status signals flow from data path to controller. Q0, the LSB of the multiplier, determines whether an addition is needed this cycle. P0 from the counter indicates all iterations are complete. Start is an external signal initiating the operation, and carry from the adder is used during shift operations. On the right, our control signals flow from controller to data path. Load_eggs loads the initial values into all registers. Add_eggs enables the adder. Shift_eggs performs the right shift. Decr_ decrements the iteration counter, and done or ready signals completion externally. Every signal on this slide will reappear in the ASM chart and again in the HDL. This is the vocabulary the rest of the lecture is built on. Now let's see these exact signals appear inside a real ASM chart. This is step 4 of our methodology, the detailed ASM chart. Once the data path exists, We go back and replace abstract RTL notation in our ASM chart with the actual signals the datapath defines. Trace it left to right. Idle asserts ready and waits on the status signal start. Once start fires, load asserts load_eggs, initializing the accumulator, carry, multiplicand, multiplier, and counter. Shift then asserts shift_eggs on every iteration, shifting C, A, Q right by 1 bit. The decision P equals 0 checks the counter. While it's still non-zero, we drop down to check Q0, and only if that bit is 1 do we assert add_eggs in the ADD block before looping back to shift. Once P equals 0, we assert done and finish. This is the shift and add multiplication algorithm, expressed entirely in ASM notation with real signal names instead of pseudocode. We've now got a complete, detailed ASM chart for the datapath side. Let's turn to the other half of the system. How do we actually design the controller that generates these signals? There are two fundamentally different ways to build a controller. Method 1, hardwired control. You assign binary codes to your states, build a state table, essentially a truth table for next state and output logic. Derive minimized Boolean equations using Carnot maps, and implement those equations directly in gates and flip-flops. This gives you optimized, fast, minimal hardware, but it's complex to design, and any change requires new hardware. Method 2, microprogrammed control. You store the control logic in ROM or RAM, using the current state plus inputs as the memory address, with the ROM's data being the concatenation of next state and outputs. Every clock cycle, you simply read the ROM. This is easier to modify, since you just change memory contents, and it has a very regular structure, but it can be larger and slower than custom logic due to the memory access delay. Let's see hardwired control worked all the way through on our multiplier example, starting with assigning states and building the transition table. For our multiplier controller, we need just 3 states. Idle, coded 00, waits for the start signal. MUL0, coded 01, checks the multiplier bit and maybe adds. And MUL1, coded 10, shifts and decrements the counter. The transition table on the right captures every possible combination. Idle stays in idle while start is 0, and moves to MUL0 once start is 1. MUL0 moves to MUL1 when Q0 is 0, but stays in MUL0 when Q0 is 1. That's the cycle where the addition happens before continuing. MUL1 returns to MUL0 while P0 is 0, and moves to done, then back to idle, once P0 is 1. This table is nothing more than the ASM chart from a few slides ago, rewritten in truth table form. And a truth table is exactly what we need to derive Boolean equations. From this transition table, we can now derive the actual next state and output equations that get implemented in gates. Reading directly off the transition table, the MSB of our state, M1, is 1 exactly when we're in MUL0, state 01. The LSB, M0, is the OR of 2 conditions: being in idle with start asserted, or being in MUL1 with P0's complement. Meaning we haven't finished counting yet. On the output side, load_eggs fires when idle and start, add_eggs fires when MUL0 and Q0, shift_eggs and decra both fire simply whenever we're in MUL1, and done fires whenever the state equals done. The block diagram on the right shows how this all fits together physically. Start, Q0, and P0 feed into next state logic alongside the current state register. That logic feeds an output decoder that produces our control signals, and the state register itself updates on every clock edge. This is a complete, synthesizable hardwired controller derived directly and mechanically from the ASM chart. That's the hardwired approach in full. Let's contrast it with the memory-based alternative, microprogrammed control. Microprogrammed control stores binary control values as words in memory rather than wiring them into gates. 3 terms matter here. A microinstruction is a single control memory word that specifies the control signals for one state. A microprogram is the full sequence of microinstructions, and control memory is the ROM or RAM holding them all. Look at the diagram. The current address feeds into control memory, which outputs a microinstruction. That word splits into next address information and a control register's worth of actual control signals, both of which loop back based on status signals from the datapath. The advantages are significant. You get flexibility, since changes are just memory edits rather than hardware redesign. A very regular, structured layout, built-in debugging, since you can literally read and write control memory, and easy expansion. Adding new operations just means adding new microprograms. Whichever control method you choose, you still need to be precise about one more thing. Exactly when your outputs are allowed to change. That's the Mealy versus more distinction. This distinction is subtle but critical for correct hardware synthesis. A more output depends on state only, and it's asserted throughout the entire state. In our diagram, state S0 asserts Y and YB for the whole time the machine sits in S0. A Mealy output depends on state and inputs, and it's only asserted when a decision box's condition is true. In the diagram, Y1 and Y2 only fire when we're in S0 and the input X equals 1. Why does this matter so much? More outputs are registered. They're synchronous and change cleanly on clock edges. Mealy outputs are combinational. They're asynchronous and can glitch mid-cycle if the input changes at the wrong moment. This affects both your timing analysis and exactly how you write your HDL. More outputs typically live in a clocked always block, Mealy outputs in a combinational one. Let's now put every concept we've covered, Datapath, ASM chart, hardwired control, Mealy and more, together in one complete worked example. Let's fully specify our running example. A 3-bit multiplicand, a 3-bit multiplier, producing a 6-bit product, using the sequential shift and add method with a single adder. The datapath needs a 3-bit accumulator A to store the partial sum, a 3-bit multiplier register Q that shifts right each cycle, a 3-bit adder to add the multiplicand into the accumulator, a 2-bit counter, since log base 2 of 4 is 2 bits, covering our 3 iterations, and a 7-bit shifter handling the combined C, A, Q register. Every dimension here follows directly from the bit widths we chose at the top of the slide. This is the kind of sizing exercise you'll do at the start of every real datapath design. With the datapath sized, let's define exactly what signals cross into and out of the control unit for this specific design. For this specific 3x3 multiplier, the control unit has exactly 3 inputs and 3 outputs. Inputs: start, an external signal that initiates multiplication, LSB, which is Q0, the least significant bit of the multiplier register, coming from the datapath, and CNT_done, from the counter, indicating all 3 iterations are complete. Outputs: shift, which enables a right shift of C, A, Q in the datapath. Add, which enables addition of B into A. And done, an external signal marking multiplication complete. The diagram at the bottom makes this concrete. 3 inputs flow into the control unit FSM, 3 outputs flow out to the datapath. This is the exact interface we'll implement in HDL 2 slides from now. With the interface locked down, let's look at the complete ASM chart that implements this exact behavior. Reading this chart left to right. Idle holds done at 0 and waits on start. Once start equals 1, init loads the multiplicand, multiplier, accumulator, and carry, and initializes the counter. Then LSB equals 1 checks the multiplier's current bit. If 1, we detour through ADD, asserting add equals 1, before rejoining the main path. If 0, we skip straight through. Either way, we land at shift, which asserts shift equals 1 and shifts C, A, Q right by 1 bit. From there, CNT_done decides whether we loop back to check the next LSB bit, or fall through to done, asserting done equals 1, and returning to idle. Compare this directly against the state transition table from a few slides back. Idle, MUL0, and MUL1 map exactly onto the idle, LSB check, and shift states here. Same algorithm, 2 different notations. We now have a complete, verified ASM chart. Let's translate it directly into HDL for both the controller and the datapath. Notice first that the controller and datapath are separate modules communicating purely through control and status signals. That's the 2-part structure from slide 2, now realized as actual code. On the left, the control unit skeleton. A state register updates synchronously on the clock, and a case statement over the current state determines the next state and asserts Mealy or more outputs exactly as we trace through the ASM chart. Start branches out of idle, LSB branches at check_LSB, and so on. On the right, the datapath skeleton. A single always_FF block handles all register updates. Load_regs initializes everything. dec_p counts down, add_eggs performs the addition, and shift_eggs performs the shift, and the final product is simply the concatenation of A and Q. This is about as clean a mapping from ASM chart to HDL as you'll ever get, precisely because we did the design work up front. With working HDL in hand, let's verify the design is actually correct by producing a timing diagram straight from the ASM chart. Deriving a timing diagram from an ASM chart follows 3 steps. Draw the clock signal first, always. Identify the state sequence from the chart. Then determine each output based on state and decision conditions. Walking through the waveform. Start pulses high for exactly 1 clock cycle while we're in idle, which is what kicks off init on the next edge. LSB is sampled during each CHK state. You can see it evaluated twice here, once low and once high, driving 2 different paths through shift. And CNT_done stays low through the earlier shift states, only going high on the final shift. That's precisely the signal that routes the FSM into done rather than back to another CHK cycle. This is exactly the kind of diagram you'd hand to a lab partner, or generate in a simulator, to prove your controller behaves the way the ASM chart says it should. We've now walked the full pipeline from algorithm to ASM chart to Datapath to control logic to HDL to timing diagram. Let's close by pulling every piece back together. Let's recap the whole lecture in one table. Every digital system splits into a datapath that does the work and a controller that sequences it. The ASM chart is a structured flowchart, state boxes, decision boxes, and conditional boxes that maps directly to hardware. An ASM block bundles one state with its decisions and conditionals, executing entirely within 1 clock cycle. Our design flow runs algorithm, to ASM chart, to Datapath, to detailed ASM chart, to control logic. A top-down process, one manageable step at a time. Control design itself splits into hardwired, which is fast and fixed, versus microprogrammed, which is flexible and memory-based. And Mealy versus more governs exactly when your outputs are valid, state only and registered, versus state plus input and combinational. If you can walk through our multiplier example from algorithm to working HDL without referring back to your notes, you've mastered today's material. That's a wrap for today.